Math 1314, Tyler Junior College, Section 1.7, Linear and Absolute Value Inequalities. Compound inequalities, and in the previous video we discussed how to solve compound inequalities when the conjunction joining them was or, and I even told you that the next video was going to be the same thing except with the word and. Now, this is the how to solve an or inequality list. When we solve this, we will adjust that to answer how to solve an and inequality. So let's solve the compound inequality. X plus 2 is greater than 5 and x minus 3 is less than or equal to 4. So now our solutions have to satisfy both original inequalities. For example, is 4 a solution? If I put 4 here, will it make it true? 4 plus 2 is 6. 6 is greater than 5. Yes, 4 makes this true. But I can't call it a solution yet because it has to make this true and this true. If I substitute 4 here, 4 minus 3 is 1. 1 is less than or equal to 4. 4 is a solution of the second inequality. And since 4 is a solution of both inequalities, it is a solution of the entire problem. But we're not just going to guess numbers and hope we find them all, because you wouldn't. There would be too many to find when you include decimals. So we're going to solve it the same way we did before. Solve each one individually and figure out what to do with their individual solutions. Solving these is trivial. I wanted them to be trivial so that we don't have to focus on how to solve them. The first solution is x is greater than 3. The second one is x is less than or equal to 7. So we need the numbers that are greater than 3 and at the same time less than or equal to 7. Well, let's sketch the number line and see if we can figure out what to do with these solutions. Since we have two numbers we're looking for, we need to make sure they're in order. The lesser number on the left, the greater number on the right. So 3 on the left, 7 on the right. The interval for x is greater than 3, or rather the number line for x is greater than 3. Greater than 3 is to the right of 3. And on the 3, since it doesn't say or equal to, we don't include it, so we use a parentheses opening towards the right. For x is less than or equal to 7, the numbers less than 7 are to the left of it. And because it says less than or equal to, 7 is a solution of the second inequality. We want to include it in our interval, which means we need a bracket on it. So now we have the individual solutions, and let's find the solution of the compound inequality. We need the values that simultaneously make x greater than 3 and x less than or equal to 7. Visually, we need the portions of the number line that belong to the red interval and the blue one. Well, wait a second. Isn't that just where they overlap? And haven't we played this game before? Absolutely. To solve an and inequality, your first step is to solve each inequality individually. But this time, instead of finding the union of their solutions, we need to find the intersection of their solutions. Because the intersection is what they have in common. And we need the values that these have in common, since it says and. So, where do they overlap? Between 3 and 7. Is 7 part of the solution? Well, does 7 make both of these true? Yes. We keep the 7. It has a bracket. This poor 7 is getting run into by everything. What about the 3? Is it part of the solution? I don't know. Does 3 make this true and this true? No. It makes the second one true. 3 is less than or equal to 7. But it doesn't make the first one true. 3 is not greater than 3. So we don't want 3 as part of the solution, which means the 3 gets a parentheses, and our interval is parentheses 3, 7, bracket. So, to summarize ands and ors before I show you one more example, to find the solution to an or inequality, solve both of them and take the union of their solutions. To find the solution to an and inequality, solve both of them and take the intersection of their intervals. And what was the last thing I wanted to show you? Well, it's an and inequality, but it's a variation on it. In the very first video of this series, when we introduced interval notation as a consequence of number lines, which were consequences of inequalities, we saw some inequalities that had an x between two numbers. That's technically a compound inequality. For example, let's consider this one. Excuse me. 7 is less than or equal to 2x minus 3, which is simultaneously less than 17. This is what I affectionately call a run-on inequality. It's like it doesn't know when to stop. But it really is an and inequality, because here's the two things the 2x minus 3 has to satisfy. 7 must be less than or equal to 2x minus 3. And at the same time, 2x minus 3 must be less than 17. So in other words, this is equivalent to 7 is less than or equal to 2x minus 3, and 2x minus 3 is less than 17. So we could split this into its two inequalities. Be careful solving this one since the x is on the right. Solve each one, find the intersection of their solutions, and that would be the solution to the original compound inequality. But think about the moves you would do to solve both of these. Since both x's are dressed up the same way, 2x minus 3, 2x minus 3, I would be performing the exact same moves on both sides of both inequalities. I would add 3 to both sides, then I would divide both sides by 2. If I'm going to solve both of these using the exact same moves, there's really no reason I needed to take them apart in the first place. I can just solve them simultaneously. For example, if I wanted to start solving for x, I would start by adding 3. And normally what I add to the right, I would add to the left. Or what I add to the left, I would add to the right. But in this run-on inequality, there is not just a left and a right. There's a left, a right, and a middle. So we can tweak the rule to whatever we do to the middle, we have to do to both the left and the right. So we'll add 3 in all 3 locations in this run-on compound inequality. 7 plus 3 is 10, less than or equal to. Bring down the 2x. The minus 3 and plus 3 cancel. Less than 17 plus 3 is 20. And the same thing for the last move. Instead of whatever we do on the left, we do on the right, the rule here is whatever we do in the middle, which is divide by 2, we'll do on both the left and the right. So 10 divided by 2 is 5, is less than or equal to, the 2's cancel in the middle, leaving the x, that was the goal, is less than 20 divided by 2 is 10. So you're just solving both equations simultaneously. And we still have to do the number line in the interval. But the number line for the solution to a run-on inequality is easy. Write your two numbers. They should be less or on the left, greater on the right, otherwise we have a problem. The x is literally between the two numbers, so we're going to shade between the two numbers. Shade from 5 to 10. And make the same decisions about brackets and parentheses. Since it says 5 is less than or equal to, we include the 5 and put a bracket on it, opening towards the right. And since it says x is less than 10, we don't include the 10, we put a parentheses on it, opening towards the left. And so our interval is bracket 5, comma 10, close parentheses. So a run-on inequality, which is really just an and inequality where the right end of the first inequality matches the left end of the second, is really easy to solve. Just do moves in 3 places instead of 2, and when you get to the end, shade between the two numbers the x's between.